In a distant solar system, an amazing discovery. The first planet to be found that's very like ours. The American Space Agency released this artist's impression of a world that could conceivably host life. An amazing discovery to tell you about. The Space Agency says it has found what it's calling Earth's cousin, the most similar planet to our own they've ever found. It is certainly the strongest sign we have seen yet. That can't be denied. So I can realistically say that we could confirm this signal within 1 or 2 years. K2-18B is 2.5 times the size of Earth, and it's 700 trillion miles away. The James Webb Space Telescope is so powerful it can analyze the chemical composition of the atmosphere from the light that passes through it from the small red star it orbits. Its chemical signature seems to suggest that it contains molecules which on Earth can only be produced by living organisms. And it's such a strong signal that, if it is home to life, it's plentiful. From UFOs to possible alien abductions, we're fascinated by the idea of extraterrestrial life. Now, scientists have found the strongest evidence yet that a planet 124 light-years away could be home to life. Researchers detected molecules in the atmosphere of K2-18B, which, on Earth, are produced by marine organisms. Could this be the moment we first glimpsed signs of life beyond Earth? In a groundbreaking discovery, the James Webb Space Telescope has detected chemical compounds in the atmosphere of a distant exoplanet that may hint at alien biology. The planet K2-18B, located 124 light-years away in the constellation Leo, is now at the heart of what could become one of the most transformative moments in space exploration. 2 compounds typically found on Earth in connection with life dimethyl sulfide, DMS, and dimethyl disulfide, DMDS, were detected. While not definitive proof of alien life, the finding has ignited global scientific curiosity. The discovery points to chemical whispers from a distant world. The James Webb Space Telescope, often called the successor to Hubble, is transforming our ability to explore the cosmos. In a recent study led by Professor Niku Madhusudan from the University of Cambridge, Webb turned its infrared gaze on K2-18B, a Hycean world, a type of exoplanet believed to host oceans under hydrogen-rich skies. These planets are emerging as strong candidates in the hunt for life, due to their potential to support liquid water and maintain stable climates. As K2-18B passed in front of its red dwarf star, Webb captured starlight that had filtered through the planet's atmosphere. By analyzing how different wavelengths were absorbed, scientists were able to detect the presence of specific molecules. What stood out were chemical signatures that matched DMS and DMDS. This is highly significant. On Earth, DMS is produced almost exclusively by marine phytoplankton, and DMDS is linked to the breakdown of organic matter. Their presence in a distant planet's atmosphere is a tantalizing hint that biological processes could be occurring. Even more striking is the strength of the signal. The concentrations appear to be thousands of times higher than those typically found on Earth, suggesting either an incredibly active biosphere or an entirely unfamiliar mechanism. The detection reached 3 sigma statistical confidence, meaning there's only a 0.3% chance that the signal is a fluke. While this is robust by astronomy standards, it's still below the 5 sigma threshold, often used in physics to confirm discoveries with high certainty. This is the strongest evidence to date for biological activity beyond the solar system, said Professor Madhusudan. Decades from now, we may look back at this point in time and recognize it was when the living universe came within reach, but not so fast. Can molecules mislead us? Despite the excitement, many scientists are urging caution. The universe is full of surprises, and chemistry can sometimes imitate biology in unexpected ways. One major concern is that neither DMS nor DMDS is uniquely biological. While they're considered biosignatures on Earth, scientists like Dr. Nora Henney from the University of Bern point out that DMS has been detected on comets' lifeless icy bodies in our own solar system. We would have to strictly rule out all the other options before claiming life. She warns, there's also uncertainty surrounding K2-18B itself. While Madhusudan's team argues the planet could be an ocean world, some models suggest it might be more like a mini Neptune with no solid surface, or even host oceans of magma instead of water. These conflicting interpretations make it hard to determine whether life could even exist there. Abiotic processes could also be responsible for the observed molecules. High-energy conditions, such as volcanic eruptions, lightning, or hydrothermal vents might produce DMS and DMDS without life. The intense radiation from K2-18B's red dwarf star adds further complexity, possibly fueling exotic chemical reactions in its atmosphere that we don't yet understand. Another theory proposes cometary delivery. DMS or its precursors could have been brought in by frequent impacts. But to account for the observed concentrations, this bombardment would have to occur at an implausibly high rate, which most experts consider unlikely. Dr. Joe Barstow of the Open University sums it up. My skepticism dial for any claim relating to evidence of life is permanently turned up to 11, not because I don't think life is out there, but because the burden of proof must be very, very high. That burden, often associated with a 5 sigma statistical threshold, has not yet been met. There's also a philosophical angle to this debate. Dr. Geraint Molly from the University of Texas at Austin suggests that more definitive evidence might come not from chemistry, but from unmistakable signs of intelligent life like artificial light patterns or deliberate radio transmissions. Such technosignatures, while far less likely to be discovered, would be nearly impossible to misinterpret. Regardless of the final verdict on K2-18B, the discovery is changing the way we approach the search for life in the universe. This marks the first time that potentially biological molecules have been identified in the atmosphere of a planet orbiting in the habitable zone, and it's not even an Earth-like world. This brings the concept of Hycean planets into the spotlight. These are large, water-rich worlds with hydrogen-dominated atmospheres, likely covered by vast global oceans. They differ significantly from rocky planets like Earth, but their stable conditions and abundance of liquid water could make them just as habitable, if not more so. Intriguingly, recent estimates suggest Hycean planets might be more common across the galaxy than Earth-like ones, dramatically expanding our list of potential life-hosting candidates. Central to this exploration is the understanding of biosignatures measurable, substances that suggest biological activity. Scientists don't just look for a single molecule like DMS. Instead, they evaluate its context, its concentration, how it interacts with other gases, and whether it forms part of a chemical imbalance. That can't be easily explained by non-living processes. For instance, the simultaneous presence of oxygen and methane on Earth is a powerful biosignature because these gases naturally destroy each other unless continuously replenished by life. But biosignatures aren't infallible. Volcanic gases, comet impacts, and other abiotic processes can sometimes create similar chemical patterns known as false positives. To guard against this, scientists rely on sophisticated climate modeling, comparative data from multiple exoplanets, and simulations of exotic chemistry to ensure accurate interpretations. When biosignatures alone don't provide clarity, the search turns to technosignatures evidence of technology or intelligent life. These include artificial light emissions, laser pulses, or clusters of satellites in orbit. Any detectable feature that would strongly suggest deliberate engineering. Organizations like SETI, the Search for Extraterrestrial Intelligence, are dedicated to finding these kinds of signals. While the odds are long, the payoff would be conclusive. Looking ahead, The detection on K2-18B is only the beginning. The European Space Agency's ARIEL mission, launching in 2029, will examine hundreds of exoplanet atmospheres, many of them Hycean. It will provide deeper insights into planetary climates, compositions, and potential biosignatures. NASA is also developing the Habitable Worlds Observatory, a next-generation space telescope expected in the late 2030s. It will be capable of directly imaging Earth-like planets and identifying signs of life through reflected light, weather systems, and possibly even seasonal changes. Further in the future, visionary concepts like the Life Interferometer for exoplanets may allow us to not only detect biosignatures, but to map the surfaces of distant worlds, spotting oceans, continents, vegetation, zones, and daily rotation patterns. This would usher in a new era of exoclimatology, the science of studying the climates of other planets in detail. Ultimately, K2-18B is more than just another planet in the sky. It represents a turning point in astrobiology, showing how far our instruments and our curiosity have come. If life is out there, discoveries like this one are bringing us ever closer to finding it.